Hi everyone, my name is Armando Soares. I am a PhD student in computer science at Federal University of Ceará from Brazil. My advisors are Lincoln Rocha and Ricardo Brito. I would like to introduce our study. What code artifacts indicate architectural technical debt? An exploratory case study in Apache Cassandra. It's important to know the context of our study and some critical concepts. There is a natural pressure to provide quality and controlled costs in large-scale software systems. A large number of integrated components, models, subsystems requires a more complex software architecture to ensure the sustainable growth of large software systems. However, a new features are added and detected are corrected. It's necessary to control the effort spent on maintenance and evolution of the software system. So we can observe that systems that grow without a well-established architecture tend to degrade over time. For example, we can find anomalies like both mud and architectural patterns. A type of technical debt that is currently standout is architectural technical debt, which refers to violation of good architectural design practice, violation of architectural integrity, or even implementations of immature architectural designs. Finally, uh, architectural smell can be seen as the cold smells metaphor at the architectural level that can be used to indicate ATD. What are the problem and motivation of our study? In the software development lifecycle, about 36% of all maintenance effort is spent on technical debt. The most critical technical debt is architectural technical debt. So, the most challenging aspect of ATD is its identification, also the ATD measurements and the process of management. What's the purpose of our study? The goal is to establish a systematic method to automate the detection of source code artifacts and version control that indicates the presence of ATD. So, how to achieve the goal? We want to define a method that generates indicators of ATD through the history analysis and source code changes in the software code over time. The research questions. For this, we defined three research questions to guide our study. First one, how to identify code artifacts that may indicate the presence of ATD. By answering this question, we can check the methods, the source code files identified by methods, and which characteristics generate a lot of maintenance effort and many recurrent changes over time in source code using architecture smells and code metrics. The second one, how do ATD related code artifacts impact other code artifacts over time? By answering this question, source code files with many recurrent chains and causing chains to propagate to other files that depend on it can aid in refactoring impact and planning how to pay the ATD item. The third one, to what extent does the maintenance effort of ATD-related code artifacts differ from other code artifacts? Finally, by answering this question, it will be possible to know if the magnitude of maintenance effort spent on the set of these files over time is substantial concerning maintaining the project as whole. The proposition and hypothesis. During our ATD studies, we have observed a particular pattern in source code artifact over time. That is, they tend to change frequently and produce recurrent effort. Based on this, we made the following proposition. There are two main aspects. An ATD item must impact the software at architecture level, and the ATD item must be a technical debt. That is, the incurrence implies an extra and recurrent maintenance effort throughout the software lifecycle. Based on our proposition, we define the following hypothesis. Source code files that indicate the presence of ATD are files that have the following characteristics. First one, impact on the software architecture of the system. Second two, constantly changed together with other source code files over time. Third one, generated a recurrent for to be maintained. And finally, propagate induce recurrent changes in other source code files. To check our hypothesis, we choose to perform a case study on a complex software repository actively maintained by the community and with over 10 years of active development on GitHub. To chosen project, the chosen project was Apache Cassandra. The items extracted was related to commits from version 3.0.0 to 3.11.11. We select the range of 3.x because it's still the most used version by community, according to Apache Cassandra site. The data was related to modified files with architecture smells, more specifically about cycle dependence and hub-like dependence. Also, we analyzed about 5,559 commits in this range of commits analyzed. We considered Java files from folder source java org apache/cassandra. From this first version, we analyzed about 1,243 files. Also, we analyzed about 1,520 files from the last version. Okay. Talking about data collection and data analysis. For data collection and data analysis, we define the following process. We try to explain about 7 stages. The first stage, we get commits and files modified for each commit. Stage 2, from each file, we calculate accumulated modifier lock, file occurrence in commits, and cyclomatic complexity. In stage 3, we generate a scatter plot regard to accumulated modifier lock and files occurrence in commits. Stage 4, we generate a dependency matrix that correlates dependence among Java files analyzed. Stage 5, we select critical files with highlighted points from scatterplot with high cyclomatic complexity and cycle dependence and hub-like dependence. Stage 6, we select files that depend on critical classes and have code change with critical classes. Finally, in the last stage, we generate a detailed report about selected files. Okay. Talking about the results. For RQ1, we use the concept of architecture smells, more specifically cycle dependence and hub-like dependence, to select initial sets of source code files, supposedly related to architecture problems. Next, we performed a change analysis on candidate to identify what files are changed together recurrently. After that, we used code metrics to evaluate the source code file's growth in size, and complexity over time. Finally, we found 12 source code files that was called critical classes that may indicate the presence of ATD with the analyzed commit range. Hence, these critical classes have cycle dependence, hub-like dependence, high file frequency in commits, high number of accumulated modifier locks, and high number of cyclomatic complexity that can indicate the presence of ATD. As we can see in the scatter plots that represent the relation between accumulated modifier lock and files occurs in commit, we can observe the critical class in quadrant 1, that is, high number of accumulated modifier lock and high number of files occurs in commits. As we can see in the table the 12 critical class increase in lock and cyclomatic complex over time. About the arcquit 2, the 12 critical class impacts on the 251 files because this class depends on critical class and have got change with critical classes. So we can observe that all these 263 files are increasing accumulated modifier locks, cyclomatic complexity, and have a high frequency in commits. Finally, we can observe that the critical class and files impacted by critical class may indicate the ATD accumulation. Finally, the result of arcquit 3 we have when we consider all Java files from main folder analyzed, we found that the forward span on ATD represents about 1961% related to a forward span in modifier locks for each file. Furthermore, if we consider on the core implementation files, we found that the forward span on ATD represents about 32 to 1% related to a forward span in modifier locks for each file. Hence, we can observe a high effort of ATD in the critical class and its impacted files. Finally, we get the following conclusions. Source code files with cycle dependence, hub-like dependence, frequent mod file that show increasing growth in lock, and cyclomatic complex over time can indicate the presence of ATD. These files tend to affect many other dependent files that have frequent change over time. Also, our finds suggest that it's possible to use only information from source code artifacts on the version control to identify the presence of ATD systematically. Our study can be replicable by researchers, as we can see in the replication kit published in our GitHub. And regarding particulars, we provide an automated method based only on the source code repository analysis that can help evaluate critical files that indicate software architecture that calls ATD. So this method can be reproducible, providing user information about source code files that cause an expensive effort maintenance in architecture of the system. Thank you very much. Feel free to ask anything.